Okay, I'm going to go over this exam, first 5 problems. Looking at problem 1, in order to get full credit, I'm going to want you to write down this definition I have for unbiased. I know a lot of you guys know what it means, but some of you guys might not. So looking at this question, it says a survey is to be conducted in a small upstate village to determine whether or not local residents should fund construction of a skateboard park by raising taxes. Which segment of the population would provide the most unbiased responses? Now, if you look, unbiased, if you look at the definition and it says showing no prejudice for or against something, or being impartial, you can see that answer 1, if you are a skateboard enthusiast, which means you really like skateboards, you don't have an unbiased opinion. Most likely you are going to vote for a skateboard park. A senior citizen living on a fixed income who does not skateboard, which is our answer 2, is most likely not going to vote for. They're probably going to be biased, have a bias against the skateboard park. So that would not be a segment that would be unbiased. A group opposed to any increase in taxes, well, obviously they're not going to want something like that because it's going to increase their taxes. But if you look at number 4, it just says every 10th person 18 years of age or older walking down Main Street. Now, that is going to be a random sample because that 10th person walking down could be a skateboard lover. They could be someone who doesn't like skateboards. They could be an older person, a younger, so you're going to get a random sample, which is going to be an unbiased sample. So number 4 is going to be your answer there. Number 4. All right. Okay, looking at number 2, we talked about number 2 in class, but I'm going to want you to show some type of work with a unit circle. So if you have an angle which does not, so what the question is which angle does not terminate in quadrant 4 when drawn on a unit circle in standard position? So remember we have quadrant 1, 2, 3, and 4. So if we want to know which one does not, well, let's go from 1 to 4 and see which one. So if we have going negative 300, that's going to be going around this way. So remember, if you have, let's go ahead and make our initial and our terminal vector. All right, so we have, if we go all the way around here, that's 90 degrees right there, negative 90. So if I keep going, that's negative 180. This is negative 270. Now, somewhere in here is going to be negative 300. So it looks like that's going to be my answer, but let's look at the other ones. So that should be around where negative 300 is. Well, let's look at the other ones here. All right, so if you go for number 2, if you go negative 50, remember, negative 90 would be here. So it's going to be somewhere in here. So you're probably looking about, give or take there. And that definitely ends in quadrant 4. Then if you go positive 280, well, remember, you're going, that's 90. That's 180. This is 270. And 280 obviously would be about right there. So that's in the 4th quadrant. And then the one that confuses students is the last one. If you're going positive 1,030, you have to count by 360s each time you go around. So if I go around once, that's 360. If I go around again, that's 720. Now let's see. So let's now go by 90. So I'm at 720. So if I go here, 720 plus 90, that's going to be 810. Another 90 here is going to be 900. Another 90 here is going to be, I'm losing track now, it's going to be 1,000, I believe. And then 30 more would be in here, which would also end in quadrant 4. So our answer is number 1. All right, number 1. All right, for this one, you're just going to want to write down the work that I have here. This is a complex fraction. You have a fraction on top of a fraction. If you remember when we did this in class, I told you the best way to do it, or the way I would do it, not necessarily the best way, but the way I would do it is to make the top one fraction and the bottom one fraction. Well, the bottom here is already one fraction, but the top is not. So we have to combine 1 over x plus 3 over y. We want to have that be one fraction. So a common denominator in this case would be xy. So I'm going to have xy here, and then xy here. And I'm only dealing with the bottom, with the top rather. The bottom I'm leaving by itself right now. So looking here, if I look at this first one, which is 1 over x, what did I have to multiply this by? What did I have to multiply the bottom by to get xy? Well, I had to multiply it by y. So I had to multiply by y over y. So y times x here would give me yx, and then y times 1 is just y. So I'm going to write this again down here. So this I turned into y over xy. And then this other one, I'm going to multiply this by x over x, which is going to end up being 3x over xy. So we're going to have y over xy plus 3x over xy. And what I told you is typically if you have one denominator, in this case it's going to be helpful to write this as one fraction, which you can do when you have the same denominator. So we're going to write this as y plus 3x all over 3y. So we changed that top. So now we're going to go ahead and deal with it. So I'm going to change colors now. So I'm going to have y plus 3x all over 3y. Now that's my top. It's one fraction now, which is what we're looking for. All of that over this part, which is 2 over xy. Now I like to rewrite this side by side, because for some reason I just like it that way. You don't have to do it, but I like it that way. Remember, this line means division. So I could rewrite this as, I'm going to erase some stuff here. Okay, I'm going to rewrite this as, I'm going to change colors again. So I'm going to have y plus 3x over 3y. I'm taking a second here to make sure I'm doing this. 1 second. Okay, made a mistake in my writing. It's over xy. All right, so be careful there. And I'm going to divide that by 2 over xy. All right, remember when you divide fractions, you change the division to multiplication, and you flip or take the reciprocal of the second fraction. So I'm going to have y plus 3x all over xy times xy over 2. All right, so let me move that multiplication so actually, there we go. All right, so now when you're multiplying, you can cancel across, not across, diagonally. It has to be with something on the top, something on the bottom. So you don't want to cancel across. I shouldn't have said that. You want to cancel top with bottom. So you can, in this case, cross cancel. It's going to give you 1. So you're going to end up with y plus 3x all over 2, because 2 times 1. And We have answer 4. There we go. All right, for number 4, your answer is number 3. Hopefully you will get that one right. We've talked about that. The reason why it doesn't represent a function is because you have 5, which this would represent your x and your y, or maybe input, output. But whenever you have a situation where an input goes to 2 different outputs, it's not going to be a function. If you actually graph this, it would not pass the vertical line test, because if you went to 5 on the x-axis, it would correspond with 4 and 6, so it would not pass the vertical line test here. All right, your answer for number 5 is going to be 4. I'm not going to go over this too much. We will be doing probability in the future. I don't want to get too much into this, but I do want you to understand where these numbers came from. So it asks, which expression represents the probability of the spinner landing on B exactly 3 times in 5 spins? So you're dealing with combinations, first of all, and you have combinations versus permutations. Right? And as you can see here, this little C here is talking about combination. And when you have this 5, this is talking about how many times you're going to spin. This 3 is talking about how many times you want it to land on what you're trying to figure out the probability. So if you're talking about B, that's going to be the one you're trying to see how many times it'll land on B, or no, you're not trying to see how many times. You're trying to see what the probability of it is landing 3 times. So that's why you have the 3 here. And the 1/8, think about where that 1/8 comes from. Well, there's only 1 B on here out of 8 possibilities. That's where this 1/8 comes from. The 7/8, hopefully you can figure out that there's 7/8 of a chance that it won't land on B, right? So that's where all these numbers come from. I do want to show you in the calculator how you can get the combinations versus permutations, and I'll do that in just a second. I want you to write down these definitions of I want you to write down these definitions of a combination versus a permutation. And basically, with a permutation, order does matter, and with a combination, it doesn't matter. And there are a lot of examples. Even though your locker combination, it's called a locker combination, but really it's a permutation, because if your locker number is 15, 6, and then 30, the order you do that in matters. So you can't go 36, 15 and expect that your locker is going to open. So really it's actually a permutation. And if you want to figure out how many, well, let's give another example. Maybe this will be easier for you. May or may not. If you have, say for instance, you have 5 players who are going to be on the floor in a basketball game, and their names are Tom, Bill, Andy, Jeff, and who's in my first period class? Antonio. Okay, so I have 5 people. Now, if they went to go sit down on chairs, they could go in a lot of different directions. Not a lot of different directions, but a lot of different orders. So you could have Tom be first, and Maybe the next time they go sit down, it's Tom, and then Andy, and then Jeff, and then Bill, and Antonio. This would actually be a different permutation, but it wouldn't be a different combination. You see, because in both cases, the same 5 guys are going to be sitting down in those chairs or going on the floor to play. So the fact of where they sit in the chair is not going to matter. But if you're talking about permutations or what places they can sit in the chair, now you could keep going for a long time. I mean, you could have Tom be in the first chair, but instead of Andy, maybe Jeff is in the second chair. And then Bill, Antonio, and Andy. That's another permutation. If you actually go to the calculator, you could do, let's see, I'm going to do a combination. So if I do a combination, I'll go 5, then I hit math. There might be a quicker way to do this. If there is, go ahead and do it that way. But if I want to find a combination, how many possible combinations are there when you have 5 and you do 5 and choose 5 out of those 5? It's going to be just 1. There's only one combination. It doesn't matter because the order doesn't matter. Now, if you were to do the same thing, but you were to figure out the permutations of those 5 in order matters, now I'm going to do 5, and let's see, go back to math. Then I'm going to go over to probability, and I'm going to do 5, choose 5 here, and hit enter again. Now, do you see how many more possibilities there are? So that's the difference between permutations and combinations. Just a basic, we're going to talk about that more, and, before I teach it, I'm going to go, look into it a little bit more, so we can have a good unit on it. But that won't be for, another month or 2. So that's the first 5 problems. I'll have another 5 up by most likely Wednesday.